So yesterday we had seen the applications of summing amplifier, right? And we had also seen as to how this summing amplifier works, even though we have more number of input terminals, right? So here we had seen that R1, R2, R3 were given, and our output voltage was exactly the average of all the three input voltages V1, V2, and V3, right? So that was the equation that we saw. So since this was in the inverting configuration, we have a minus, right? So V1, V2, V3 divided by 3, right? So today we'll be looking into the non-inverting configuration of the summing amplifier. Now, just like we had seen the inverting form, here we have the non-inverting form, okay, wherein it's connected to the plus terminal, right? And we have resistors R1, R2, and R3 and R4. As you all know, R3 and R4 forms a combination called, what is it called? R3 and R4 forms a combination, right? And that is called?
Voltage divider.
Very good. That's called a voltage divider. So using these previous concepts and the present concepts, so what we will do is we will look into it as to how this non-inverting configuration actually works, right? Okay. Fine. Just give me a moment. Okay. So we will just see as to how this actually works out. So you can see that here, okay, as I was mentioning, we have resistors R1, R2, okay, R1, R2, R3, and R4. So based on this, okay, we are going to see how the circuit works. So non-inverting amplifier can be employed as summing circuit as in the diagram, but there is one benefit, okay? Can someone tell me what is the benefit of having a non-inverting configuration than the inverting configuration? There in inverting, we saw that, there used to be a minus, isn't it? But here, there wouldn't be a minus. So which means it's a direct sum, okay? It's a direct sum. Whatever is the inputs given here at the input side, you're going to get a direct sum at the output, right? Unlike the previous configuration where it was, with the minus sign, R2 by R1, fine. So equation for the output voltage can be derived by first applying, the superposition theorem and, taking VI into consideration, right? So VI is the input voltage, okay? V1 is the voltage 1 at resistor 1 and voltage 2 at resistor 2. And this VI is the input which actually gets into the op-amp, right? So I hope these parameters are very much clear. And as usual, we have plus VCC minus VE and output voltage, right? So when V2 is equal to 0, right? In the first case, let's assume we are not giving anything here, right? We are just making sure that, V2 is made 0, right? So with V2 is equal to 0, and R1 is equal to R2, which means both R1 and R2 are having the same resistance values, okay? So I will now know that the input voltage, okay, VI1 is actually referring to input voltage, okay, because of the first one, Okay, so first input voltage at the input side because of V1. Okay, so that is VI1. So VI1 is equal to, okay, whatever that we have, okay, it is going to be divided by 2 because we have two input terminals here. So hence I get V1 by 2. So I think this concept we had already studied, right? So if we have 3, then it's going to be V1 plus V2 plus V3 divided by 3, isn't it? And if we have 4, then it's going to be plus V4 divided by 4. Right? So the same concept that we are using here. So which means our VI1 is going to be V1 divided by 2. So I hope there is no doubts here, students.
No doubts.
Yeah. So advantage you should understand. We are not getting an inverted output, but we are getting the same output just like the input, but then it's a sum of the input. So this is going to be more advantageous because I don't have to consider the inverted form of input, right? It's going to be the exact summing of my input, which is appearing at the output terminals V0. Now let us take the other case. Okay, now we have taken V2 is equal to 0. Let us take V1 is equal to 0, and we will see how it impacts VI2 and what is going to be the equation. Right. So we have the same circuit here. Okay, just for the sake of convenience, I had put it up here. Okay, so that it becomes easy for us to understand, with respect to V2 and VI1. Okay, so now let's concentrate on the circuit here. Okay, so next, now I'm going to take V1 is equal to 0. Previously I had taken V2 is equal to 0, right? So now I'm going to take V1 is equal to 0. So when V1 is equal to 0, okay, my input voltage because of V2 is going to be V2 divided by 2. So I think all of you agree with that. Yes or no? I'm keeping one 0, and at the other side I'm giving my potential. I'm giving my voltage, right? Previously I had made V2 as 0, and now I'm making V1 is equal to 0. Okay, so if V1 is equal to 0, is there going to be any I1 getting generated, current I1? Students, because potential V1, okay, if V1 is equal to 0, can I expect, okay, can I expect any current flowing in this fashion here, I1? Is it going to happen?
No, sir.
No, it's not going to happen, right? Because there's no potential at all. Ultimately, you should understand current is nothing but the potential difference, right? It's the flow of electrons. So this electrons, as I mentioned previously, they go from a higher potential to a lower potential. So since now I have not given any potential, okay, here I have not given any potential, I cannot expect any current that can pass through here, right? Fine. So my VI2, okay, is going to be the input voltage which is entering the op-amp, right, is going to be V2, whatever is my voltage, V2 divided by 2. Why 2? Because we have two terminals here. Fine. So this happens to be, right, VI is actually V1 by 2 plus V2 by 2. So my input voltage in general is going to be, please make note of this formula. My input voltage generally is going to be VI is equal to V1 by 2 plus V2 by 2. So since 2 is at the denominator, right? So I can take V1 plus V2 divided by 2, right? Now let us consider ACL, right? So what is ACL? ACL is nothing but closed loop gain. So closed loop gain, as we have seen previously, it is nothing but R3 plus R4 divided by R4. Many times we have seen. See, one thing that you all should keep in mind is most of the concepts that we have studied in first module will keep as a base, okay, for the other modules, right? So that is why, I'm trying to revise the concepts that we had done in the previous class. I'm trying to connect things between what we had done today, yesterday, and the previous classes, so that you'll be able to feel that yes, it is the same what we have studied now and what we had studied previously. So concepts remains the same, right? So we had seen this even previously, R3 plus R4 divided by R4. So the same is given here. So what I'm going to do, I'm going to now check, okay, that V naught is equal to ACL into VI. So we know that, the output voltage is nothing but input into gain. Yes or no? Do you all agree with that?
Yes.
Output voltage is nothing but gain into whatever input. So input, you're giving something that gets multiplied with the gain. So you get a higher proportion of output across V naught, right? So this is the whole idea of your amplifier, right? So the inputs are taken and it's been amplified, and then it is given at the output side. Now, since these amplification, okay, is at a very high level, so what we do, we try to connect it in the negative feedback format, right? So whereby the oscillations are reducing, whereby I'm getting a stable output and also having a form of gain, right? So coming back, here to V naught is equal to ACL into VI. So ACL, I already know it is R3 plus R4 divided by R4 into my VI. So VI is here. Okay, so this is taken down, isn't it? Right? So this one I'm taking from here, and my ACL is from here. Right? Okay. Now let us do something here. With R3 is equal to R4. So what I'm trying to do is, I'm trying to make this R3 and R4 equal. Okay. So when I say equal, I'm going to make them have the same values. Okay, R3 and R4. So if I substitute this R3 is equal to R4 here, then what is going to happen? When R3 is equal to R4, so it becomes 2 times R4 divided by R4. Yes or no? Students, please respond.
Yes, sir.
Yeah. So it becomes 2 times R4 divided by R4. So R4 will get cancelled. So the 2 also will get cancelled here and here. So ultimately, I am left out with only V1 plus V2. Is that clear, students? I suggest you please note it down, okay? Try to write it in your notebook so that you will be able to understand. See, without writing, if you just see and listen, it becomes difficult. You're using more of, understanding when you actually write and practice, okay? So I suggest you to put this R3, substitute R3 as R4. So it becomes 2 times R4 divided by R4 gets cancelled, and the remaining 2 and 2 gets cancelled. So I'm left out with V1 plus V2. So what is my output here directly? It is a sum of both inputs, which is given as V1 and V2. So there is no, any form of negation here. There is no minus, but then there is addition of both V1 and V2. So this is called your non-inverting summing circuit or non-inverting summer. Now let us check if in case I give an additional input, just like how we had seen for the inverting concept, right? So R1, R2, these all remains the same, right? So what I'm going to do is, so R1 is here, fine. R2 is also here, fine. So this is the additional thing that I'm adding, right? So I'm going to have 3 resistors. So along with 3 resistors, I'm going to have V1, V2, and V3 respectively. So my input voltage here is going to be Vi, okay, which comes across this junction here, the junction that you see here, right? Yeah, fine. And so we understand that, you know, the voltage at the op-amp non-inverting input with all 3 input resistors will be V1 plus V2 plus V3 divided by 3, right? Just like how we have, you know, the input voltage 2 is equal to V2 by 2, right? Similarly here, my input voltage is actually, this input voltage is actually going to be an average of all these 3, which is V1, V2, and V3. Let's say we are taking V1 as 5, 5, 5. Okay, so 15 by 3, so which also gives me 5. So 5 volts will be what is getting into the op-amp, right? So one more important thing, right? Very important thing. If you want exact, okay, if you want it to be exact V1 plus V2 plus V3, I have an additional 3 here, right? If my output should be exactly V1, V2, V3, just like how I have here, you know, V0 is equal to, right? V0 is equal to V1 plus V2. If I want the same format here also, V1 plus V2 plus V3, then I have an additional 3 here, right? So how do I get rid of this 3? Now we know that the output, right? The output is nothing but gain into input. So if I make my gain is equal to 3, okay, so it becomes 3 times Vi. So 3 into V1, V2, V3 divided by 3. So that 3 and 3 will get cancelled. So I will be left out with V1 plus V2 plus V3. Is that clear, students? Yes, is that clear?
Yes.
Now let's say, what if my ACL is equal to 2? What happens? How is my output voltage going to be? Take ACL is equal to 2, okay, and tell me what is my output voltage going to be? I hope you have understood my question. Any doubts, please ask. Students, you're there with me? Yeah. So what is my output voltage going to be? You know, input is nothing but V1 plus V2 plus V3 divided by 3, right? So this is fine. So we are okay with this. Now, the only change that I'm going to do is, if in case I design my circuit in such a way that I give ACL is equal to 2, then what is going to be my output voltage for the new ACL?
Same as input, sir. V1 plus V2 plus V3 by 3.
Now you have ACL is equal to 2. So if you apply this formula, V0 is equal to ACL into VI, you have to apply this formula here, isn't it?
2 into V1 plus V3 by 3.
Sorry? Come back again.
2 into V1 plus V2 plus V3 by 3.
Yeah. So you can do that 2 by 3, isn't it? So which means you're going to get approximately how much? About 0.6666, isn't it? So which means we can take it as 0.67, isn't it? So approximately we can say it's about 0.7. So 0.7 times of my input. So So it's not going to be the same. It's going to be an amplified version of input, isn't it? So if I reduce the gain, what is going to happen? At the output side, instead of just being 1, 2, 3, okay, which is V1 plus V2 plus V3, but then it's going to be 0.6 times. Okay, it's going to be 0.6. So 0.6 times 0.6 times my 0.6 times into V1 plus V2 plus V3. So I hope this is clear, isn't it? So what is happening? I am actually not getting only this V1 plus V2 plus V3, but then I'm getting an additional 0.6 here. Yes or no?
Yes, sir.
Yeah. So in order to nullify this 0.6, okay, I should make sure that my ACL is 3, so that this 3 and this 3 will get cancelled, and I will only get V1 plus V2 plus V3. So this is how you actually play around with the circuit. You make sure how much is your gain, okay, and you can reduce the gain, increase the gain. Ultimately, it's all with the value of resistances, right? Now the next question will be, sir, how do I make sure that ACL is varied? Come back to the formula here. You have a separate formula here for ACL, isn't it? So what is the formula? The formula states it is R3 plus R4 divided by R4. So which means, if you can vary this R3 and R4, now in this case, we're going to vary R4 and R5. So if I can play around with these two resistors, right, both R4 and R5. So if I can play around with these resistors, then it's going to majorly impact my ACL, isn't it? Yes or no? Is it going to impact my ACL? So if my ACL is impacted,
Yes,
ultimately my output voltage is also impacted. So resistances here, designing resistances plays a very major role, right? So you can increase this actually now. You can have another resistor R4, and then you can give V4, right? So in that case, it's going to be V1 plus V2 plus V3 plus V4 divided by 4. So in that case, what should be my gain? ACL. I should design my gain ACL is equal to
4.
4. Very good. So 4 and 4 gets cancelled. So I will only be remaining with V1 plus V2 plus V3, which is exactly doing the function of summing, right? So I hope we are clear with this concept, right? So can I move on with the next one?
Yes, sir.
Okay, fine. Please keep making note. Okay, if not, then you wouldn't understand it in a much better way. Okay, fine. So we have seen the application of summing amplifiers as to how this non-inverting summing circuit works. Okay, it's very interesting to know that these formulas do not change, right? It just remains the same. Only thing is, as soon as you see the circuit, you should be able to see and should be able to put out the formula that yes, my ACL is only dependent on these two resistors. Okay, R3 plus R4 divided by R4. So these are some of the major formulas that you'll have to remember. Your input voltage is going to be the sum of both the inputs divided by 2, V1, V2, and then your output voltage. See, we have always used this output is equal to ACL into VI, right? So there's an important note that I have written here. Okay, so that important note is design of a non-inverting summing circuit is approached first by designing the non-inverting amplifier to have the required voltage gain. So first I have to think how much of voltage gain is required, right? So now previously we saw here if ACL is equal to 2, it's going to be about 0.67 times of the input voltage, right? If I do not want that 0.67, so first I have to decide how much of ACL is needed. What is going to be my input voltage? right? So these manual calculations are a must. Once you have these values, then you can decide, okay, now based on this, based on how many inputs that I have, fine. So I'm going to have my resistor values in this fashion, R4 and R5. Okay, now I'm going to change the value of ACL. So only then, we can, then the input resistors are usually selected as large as possible to suit the type of op-amp used. So whichever type of op-amp that you are going to use, either you want a little bit of amplification or without amplification, right? So all that can be decided only if and only if first you have to decide on the ACL. Okay, first decide on the ACL, and you have to think of how many resistors do I have? Do I have 3? Do I have, am I going to increase another one, 4? Right? So all this will be taken into consideration, and then only we will be proceeding. Okay, so I hope this point is clear. Is it clear, students, what I just explained?
Yes, sir, it is.
Yeah. So
Yes.
yeah, so thinking of the gain is important. Thinking of what kind of output needed is important. Thinking of how much of resistance is needed will be based on what gain that I want, right? So how will I decide what gain, what output I need? So you can say that, the number of inputs are dependent on the number of resistors, and here the input is in turn related to the output, and the output equation is in turn, actually related to ACL. Now, if I want to vary the ACL, then it's coming back to the resistors R4 and R5 in this figure, the second figure, right? Fine. So we will move on now with the next one, which is called difference amplifier. So summer circuits are done. Summer circuits. See, sometimes what will happen, few examiners might ask exclusively, explain summer circuit keeping non-inverting configuration. So in that case, I have explained both inverting and non-inverting, right? So the one which I have done in my previous lecture is the inverting type, and this lecture is going to be, the one that you saw was about the non-inverting configuration. So either of the one when asked, okay, you can write. But if in case nothing is asked, okay, then I suggest that you go with this non-inverting type of configuration. Okay, right. So next, let us look into difference amplifier. So what is this difference amplifier? As you all know, we have two inputs, right? Inputs given at terminals 1 and 2. So when I have this inputs given at both of the terminals, it has to make sure that the differences are taken and amplified, right? So that's the job of difference amplifier. So let us look into it, and we will see what best that we can take out from difference amplifier. So a difference amplifier, or it is also called differential amplifier. Okay, so there are two terms here. Do not get confused. Okay, so difference amplifier or differential amplifier, both are referring to the same. Amplifies the difference between two input signals. Okay, so I am trying to compare two signals here. Okay, two input signals, and based on that I'm going to amplify my signals. So we have an IC op-amp. Okay, the op-amp IC is also a difference amplifier. Okay, so that's an example. It has inverting and non-inverting inputs. So we have seen this, right? So all these concepts are needed, right? The basic concepts, whatever we have studied previously, everything is needed. Okay, so it has two inputs, inverting and non-inverting. The open loop voltage gain, which is AOL of op-amp circuit, is too large, right? So too large. So what I'm going to do, I'm going to have a feedback, right? So if I have a negative feedback, then what is going to happen? The number of oscillations are going to reduce. So I'm going to get a stable output, isn't it? Right. So like the other op-amp circuits, it needs what kind of feedback? It needs a positive feedback. Now I have a question for all of you. If in case I give a positive feedback, then what is going to happen? Of course, we have discussed this in our previous lectures, but I want you to recall on the question, what happens if we give a positive feedback?
We have a very high gain, which is practical.
Correct. Very good. So the impact is going to be, how's the impact on the output signal? Is it desirable, or is it with a lot of oscillations or disturbances?
So it isn't desirable.
Oscillations will take place.
Very good. Very good. Thank you. Thank you, both of you. So that's the main reason, why we go with negative feedback. Okay, fine. So now let's look into the circuit here. Now, previously, we have seen op-amp circuits, right, which were having, which we were giving signals only at either inverting or non-inverting. But the speciality here is the inputs are given at both of the terminals, right? At the inverting terminal as well as at the non-inverting terminal. So this figure that you are seeing, it shows a combination of both inverting and non-inverting amplifiers. So do you all agree with this? Yes?
Yes, sir.
So we are giving signals both at minus terminal and plus terminal, right? So which means I can either make it as inverting or non-inverting based on the voltages that I'm going to give. If I give V1 is equal to 0, then it means it is going to be a non-inverting type. If I make V2 is equal to 0, right, then it's going to be a inverting type. Okay. If the input terminal 2, right, so this is the 2 that I'm talking about. Okay, so if the input terminal 2 is grounded, the circuit operates as an inverting amplifier, right? So with an inverting amplifier, okay, keep in mind that V1 is going to be amplified by a factor of minus R by R1. Okay, minus R by R1. When terminal 1 is grounded, okay, so when this terminal is grounded, then what is going to happen? R2 and R1 both function as feedback resistors. This is also very important. Okay, please make note of it. The first thing that you'll be making note is minus R by R1, and the second one that you'll be making note is which resistors are going to be in the configuration. Okay, please make a note. So we were looking into this differential amplifier, right, where we are taking one terminal, okay, terminal 1 when it's grounded. So the important things that you will have to note here is going to be when input terminal 2 is grounded, okay, then it's going to be minus R by R1, okay, when 2 is grounded. Now when terminal 1, when this is grounded, okay, then when terminal 1 is grounded, then what is going to happen? We are going to see that we are going to have additional resistor, okay, R1, when terminal 1 is grounded, R1 and R2 both are going to actually impact on the feedback component, right? So R1 and R2 both are going to be in my feedback component. So just in short, you can write terminal 1 grounded, R1 and R2 functions as feedback, okay, and when terminal 2 grounded, then the equation becomes minus R by R1. Okay, so these two important things that you can make note of. The input voltage V2, okay, V2 is the input voltage. So this is divided across the resistors R3 and R4. So whatever input voltage that I have here is going to be divided between R3 and R4. So that is going to be VR4, okay, the voltage across resistor R4. Okay, so VR4 is amplified by R1 plus R2, like how we saw, divided by R1. Okay, so this is happening when terminal 1 is grounded. Okay, so remember there are three cases here: terminal 2 when it's grounded, terminal 1 when it's grounded, and what is going to be VR4, okay, in the second case, which is terminal 1 grounded, right? So you will be able to understand this when you put the circuit, and point by point when you just make running notes. Okay, when I say running notes, okay, the first point that you can write is when input terminal 2, okay, when this one is grounded. So when I have this terminal grounded, then you know R1 minus R by R1 comes into picture. So when terminal 1 is grounded, when this is grounded, then R1 plus R2 adds up to the combination of my negative feedback. Right? So keep this in mind. And when I have to find out, when the first terminal is grounded, okay, then it's going to be R1 plus R2 divided by R1. So when V2 is equal to 0, okay, terminal 1 is grounded. When V2 is equal to 0, then V0 1, okay, so this V0 1 is nothing but output voltage because of the first voltage, which is V1. So this is going to be minus R2 by R1 times of V1. I think this should be R2 by R1, minus R2 by R1, not R by R1. Okay, yeah, please make it as R2 by R1, minus R2 by R1. Yeah. Fine. So is this clear now? Yes, is this clear? So we are going to take two different things here. When input terminal 2 is grounded, then it is going to be V1 is amplified. V1 is equal to, you can write V1 is equal to minus R2 by R1. Okay, when terminal 2 is grounded. Next, when terminal 1 is grounded, then you can write it as R1 and R2 is added in the feedback. Okay, next the input voltages. If I have to find out VR4 is equal to R1 plus R2 divided by R1. And my output voltage is going to be minus R2 by R1 into V1. Okay. So the last thing that we are going to see here is the continuation. Now next, when I make V1 is equal to 0, next when V1 is equal to 0, we have seen previously that when V1 is equal to 0, then VR4 is going to be R4 divided by R3 plus R4. So we have seen this previously. Now since V1 is equal to 0, it is only dependent on V2. So my VR4 is actually multiplied with VR2. Any doubts here? Any doubts here? So V1, we are taking it as 0. Okay. So let me just put a into mark here. V1 is equal to 0. So my VR4, okay. So I am looking at VR4. So this VR4 is equal to, so I have two resistors here, R4 and R3, right? R4 and R3. And what is my input? Since this is 0 here, my input is only V2. So it is dependent on V2, R3 and R4. So we know that it is R4 divided by R3 plus R4 when it is in this configuration. And the output voltage is going to be, okay, we have R1 plus R2 divided by R1, right, into VR4. So VR4 is this formula. So I just substitute, this formula here, okay, this equation here. So V02 is equal to R1 R2 divided by R1, just comes down. And VR4, I have complete VR4 here, and R4 divided by R3 plus R4 into V2. Now there's a small tricky work that you guys have to do. You have to make sure that R3 is equal to R1. So I am substituting R3 with R1 and substituting R4 with R2. Okay, so try to do this here in this above equation. So which means I'm playing only with R3 and R4, right? So R3 and R4. So this R4 becomes R2, right? It becomes R2, and this R3 becomes R1, and again I have R4, so this will become R2. Now here I have R1, R2. What is going to happen to R1, R2, students?
They remain the same, sir.
No, they don't remain, because I can cancel them. Here I have R1, R2. Here also have R1, R2. So I cancel them. Here I have R2 and I have R1. So this R2, R1 will come down here, and this V2 will come down here. Understood?
Yes.
So you should substitute here. Okay, previously it was R4, so I made it R2. Then at the bottom here it was R3. I made it R1. Okay, and this R4 was made R2. So here I have R1, R2. Here also I have R1, R2. So both gets cancelled because they are cross multiplying with each other, isn't it? And here I am remaining with R2 and R1. So R2, R1 and V2. So this is my whole thing which is actually remaining. So my output voltage here is R2 by R1 into V2. Right? Now, when I say both the signals are present, okay, so in this case we had not taken V1 and we had taken only V2. Now let us take that the next case where I give both V1 and V2. Then my output voltage, okay, this output voltage will actually change to V01 plus V02. Why is it going to change? Because I have two inputs here, okay, V1 and V2, just like how you saw the summer, right? So I'm going to have two inputs, and my output voltage, okay, is going to change, which means it's going to be a combination of both V02 and V01. We have calculated here for V02, right? So V01 also you can substitute here. So which means we have seen that previously it is minus R2 by R1, isn't it? In our previous slide, we have seen for V01. Do you all remember, students? Yes.
Yes, sir.
Yeah. So that equation we are just bringing it here. So V0 is equal to, so V02 to this full equation I'm bringing down here, R2 R1 divided by V2. Here R2 R1 divided by V1. So just see the beauty of this output voltage. Here, the output voltage 2 is dependent on R2 R1 into V2. So output voltage 2 dependent on V2. Output voltage 1 dependent on V1. But the only difference here is, since it is connected to the minus terminal here, okay, 1 is connected to minus terminal here, so I have minus R2 by R1. But here also it is R2 by R1, but it is plus, right? So understanding how it works. Yes. Yes or no? Fine. Now, since we have this formula here, okay, and what I can do is I can take this R2 by R1 as common, because here also I have and here also I have. So it becomes V2 minus V1. So how is this equation? How is it looking as?
The difference of the voltages.
Exactly. So this is an important equation. It is telling us that, you know, my output voltage is dependent on the differences between both the input voltages V1 and V2. Okay. And this R2 by R1 is nothing but your gain. Okay. The gain. R2 by R1 is nothing but your gain. Fine. Now you can just see here. When R2 and R1 are equal value resistors, the output is the direct difference of the two inputs. Yes or no? Let's say R2 is equal to 5 and R1 is also equal to 5. So what is going to happen? Both are going to get cancelled. So V0 is the direct difference of V1 and V2. Now let us say by selecting R2 greater than R1. So which means, let us say this is 5 and this is 2.5. Okay, R2 is greater than R1. So 5 by 2.5 is how much? Or 5 by 2. 5 by 2 is how much? 2.5, isn't it? So it's going to be 2.5 times V2 minus V1, just like how we saw previously. Remember, we were talking about the amplification of input based on what? Based on A, C, L. Yes or no? So here we are talking of designing these resistor R2 and R1. So when I make R2 and R1 common, both gets cancelled and I will just have V2 minus V1. When I have bigger R2 and small R1, it's going to be a small multiplying factor. Let us say it is 5 by 2. So it's going to give me about 2.5, right? 2.5 times what value? This value, which is V2 minus V1. So I will decide based on how I want to select my resistors R2 and R1. Is that clear, students?
Yes.
Yeah. So
Yes.
summer is adding, all of the inputs, and your differential amplifier is actually, minusing the inputs V1 and V2. Okay. So just make note of these formulas, make note of the circuit. Okay. It's going to be very useful for you to understand and revisit them. Okay. So shall we end our session today?
Yes.
Okay.
Sure, sir.
Thank you.